Hello viewer, welcome to Samuel Academy. In this video, I'll talk about diffraction of waves. That is the spreading out of waves when they go through a gap or past the edge of a barrier. Okay, so when waves pass through a narrow gap, the waves spread out. This effect is called diffraction. Like in this diagram, these are the waves. When they reach here, they encounter this gap, a kind of slit. So they spread out. When they come out, they spread out. Right? That effect is called diffraction. Okay? Diffraction depends on how the width of the gap compares to the wavelength of the waves. The wavelength is unchanged after diffraction. And we shall see that diffraction is more pronounced when the gap width is similar to the wavelength of the waves. Okay, let's proceed and see. We have this case where we have a wide gap and a barrier. So we want to see the diffraction of waves passing a wide gap or a barrier. So in this particular case, we find that the wide gap, this gap here, is greater in length than the wavelength. All right, so what happens? So you find that when the gap is wide, you don't have much spreading, right? So this is what happens when the waves encounter a wide gap. There is spreading, but it's not much pronounced. Okay, and here, this is a barrier, so you can see the way the spreading takes place is not much pronounced. But remember, the wavelength remains the same before and after diffraction. All right, so let's see what happens, the effect of wavelength on diffraction around an edge. Okay, the extent of diffraction depends also on the wavelength of the waves. The greater the wavelength, the greater the diffraction. So like in this case, we are seeing that when a wave goes past the edge of a barrier, the waves can curve around it. Shorter wavelengths undergo less diffraction than longer wavelengths. So this is a case where the waves have shorter wavelength. Okay, so diffraction here is less pronounced. The spreading out is less pronounced when we have short wavelength. But here, these waves have longer wavelength. So you find that the spreading is much pronounced. So this is what we are trying to put across, that what is the effect of wavelength on diffraction around an edge? So we find that shorter wavelength undergo less diffraction or less spreading, and longer wavelengths experience pronounced diffraction or spreading when they encounter the edge of a barrier, like in this diagram, right? Now next, let's look at the interference of waves. Okay, interference of waves. Two waves merge and the result can be a much larger wave, smaller wave, or no wave at all. Okay, so here we are merging two waves. So we can get the result, which is a much larger wave, a smaller wave, or no wave at all. This is the effect of interference of waves. And for interference to take place, the waves must be of equal frequency and wavelength. Right? So let's consider the following cases. We have what you call constructive interference. Constructive interference takes place when the two waves are in phase. All right? Like here we have wave X, this one here, and this wave Y. These two waves, they are in phase. We can see the crest coincides with the crest for this wave. The trough also coincides the trough for this wave here. So the two waves are in phase. So when we match the two waves, when we add the two waves, we get this result, constructive interference, because the two waves are in phase. Okay? But when the two waves are out of phase, we get what we call destructive interference. The two waves are out of phase. This wave X, this wave Y, we can see that the trough here coincides with the crest on this wave Y. And the crest here coincides with the trough. So the two waves are out of phase. So the result, that is wave Z, is destructive interference. Okay? So it is actually destructive interference. Unlike in the first case, where we have constructive interference. All right? And then let's look at interference of sound waves and something we call path difference. Okay? Interference of sound waves. So we have two speakers, L1 and L2. Now two loudspeakers, L1 and L2, are connected to the same signal generator. So this is the signal generator, and the two speakers are connected to this signal generator, so that sound waves from each of the speakers are in phase. So the sound waves from these two speakers are in phase. All right? So what happens? If we walk along line PR, this PR, along this line, PR, the intensity of sound rises and falls alternately. Hence, both destructive and constructive interference will be experienced. So this is the line I'm talking about, this line PR, this point Q. So when you walk along this line, PR, you'll experience intensity of sound rising and falling alternately. So we shall be experiencing destructive and constructive interference along this line, PR. Okay, there's a point along this line whereby, that is point Q, whereby the sound will be loudest. There will be constructive interference at this point. Okay, and this is the point where we shall have the loudest sound. Why? Because there's something we call the path difference. This is the point whereby you have maximum constructive interference, because the path difference here at Q is 0. Path difference is equal to the distance from speaker 1 to Q minus speaker 2 to Q. In this particular case, the path difference is 0. That's why we have the loudest sound produced. Now at P, the path difference is L1P minus L2P. That's how we find the path difference. The path difference at R is L1R minus L2R. So in this particular case, at point Q, the path difference, that is L1Q minus L2Q, is 0. And at this point, we have the loudest sound, where we have the maximum constructive interference. So I'm sure this video has been of value to you. So I want to request you to subscribe to my channel to be able to see more lessons in physics and other sciences. Thank you so much.